For centuries, humanity has been obsessed with mapping our world, right? Charting these unknown continents and vast oceans. But today, one of the greatest explorations isn't across land or sea at all. It's a quest deep into the very heart of matter to complete a map of the atomic nucleus itself.
So let me ask you a question. Think about all the stuff around you, the material universe. How much of what could exist have we actually found? The answer might surprise you. Turns out we've barely scratched the surface. So, how do you even begin to map something you can't possibly see? Well, physicists have a special tool for this. It's not a globe, it's not a paper map. It's a conceptual map that lays out every single possible combination of protons and neutrons, the building blocks that can form an atom. Let's take a closer look at what that means. All right, so let's start by unfolding this incredible atomic map. It's called the chart of nuclides, and it is our guide to this whole subatomic world. Just look at this thing. This chart represents every known nucleus and even every predicted nucleus. Now, all the stable stuff that makes up our everyday world, the carbon in you, the oxygen you're breathing, it all sits in that tiny, narrow little strip right down the middle. They call it the Valley of Stability. But just look at all that other space around it. That is a vast, uncharted territory filled with thousands of what we call rare isotopes. These are unstable, really exotic atoms that just flicker into existence for a fraction of a second. This is the new continent we're setting out to explore. So you've got this amazing map. How in the world do you actually explore it? Well, you have to go to the absolute edge of what's possible in modern physics. To tackle these huge questions, physicists basically follow three main paths, or frontiers. They're different ways of looking at the universe, but they all work together to paint a more complete picture of, well, everything. On one hand, you've got the energy frontier. This is all about raw power. You smash particles together at the highest energies imaginable to create totally new, heavy particles. Think about the Large Hadron Collider. That's the perfect example. But for our journey, we're interested in something different, the intensity frontier. Here, the goal isn't more energy, but just overwhelming numbers. You create these incredibly powerful, intense beams of particles to study their properties with mind-boggling precision. And this is the frontier where we hunt for those rare isotopes on our map. Now, to work on the intensity frontier, you need some seriously impressive tools. You have to build factories, not for making cars, but for making brand new matter. Yeah, you can't explore these frontiers with a simple microscope in a lab. You need these enormous, dedicated facilities, particle accelerators and detectors that are just true marvels of modern engineering. And this gives you a real sense of the incredible scale we're talking about. I mean, look at this. On the left, that's a fragment separator. It's basically a series of huge magnets that steer and sort the atoms right after they're created. And on the right, that's a complex detector array, built to catch the faintest whisper of radiation from a decaying nucleus. These are colossal machines, all designed to manipulate and measure things that are almost unimaginably small. It's amazing. And this exploration is a truly global effort. From FRIB in Michigan to facilities in Japan to CERN in Switzerland, teams all over the world are pushing these boundaries. And you can see they use different techniques. Some smash heavy atoms and pick through the fragments. Others use a target to generate specific isotopes. But they are all united in this one single quest, to create and study these rare forms of matter. Okay, so you've used a giant accelerator to smash some atoms, and you've created this chaotic cocktail of new, rare isotopes. How do you find the one specific atom you're actually looking for in that mess? Well, you need a prism, but one that's made for nuclei. The way this works is just beautiful. It's so elegant. You know how a glass prism splits white light into a rainbow? A powerful magnet does the exact same thing to a beam of mixed-up isotopes. It bends each one along a different path based on its properties. It's this incredibly simple and powerful way to sort atoms one by one. The physics principle behind this is called magnetic rigidity. But don't let the technical name fool you. It's actually a pretty simple idea. It basically asks, how hard is it to push an atom off its course using a magnet? Just like a strong wind pushes a tiny leaf way more than a heavy rock, this magnetic field bends lighter atoms a lot more easily than heavier ones. So by tuning that magnetic wind, you can precisely choose which type of atom gets to make it through. So let's just walk through it. A messy beam with all sorts of different atoms flies into the magnet at super high speed. The magnetic field kicks in and starts to bend each one. The lighter atoms get deflected on a really sharp curve, while the heavier ones take a much wider turn. Then, by just placing a tiny little slit at the end, you can physically block everything except for that one specific isotope you wanted in the first place. It is an incredibly clever filtering system. So we have gone to all this incredible trouble to create and then isolate one single type of exotic atom, which of course leads to the most obvious question. Why? What secrets do these fleeting little bits of matter actually hold?
This quote right here really gets to the heart of it. Scientists are trying to measure something called nuclear binding energy. You can think of it as the glue that holds a nucleus together. And understanding that glue is fundamental to understanding why matter, the universe, and even why we exist at all.
And here's the secret. That binding energy, it's directly reflected in the atom's mass. That's right. Thanks to Einstein's famous equation, E equals mc squared, we know that mass and energy are just two sides of the same coin. So if you can measure the mass of an exotic atom with incredible precision, you are also, at the same time, measuring the energy that binds it all together.
And this graph? This is a literal picture of E equals mc squared in action. Those two peaks you see represent the exact same isotope, manganese-52. Same number of protons, same number of neutrons. But the one on the left is in a higher energy or excited state. And because it has more energy, it literally has more mass. That tiny difference you see on the graph, that little gap between the peaks, that is the mass of pure energy. It is a perfect real-world demonstration of Einstein's theory. How cool is that?
So what's the big payoff here? Well, first, it helps us understand the cosmos. You know the gold in your jewelry or the uranium that can power reactors? All of that stuff was forged in violent stellar explosions. To understand how that happened, you have to understand these exotic nuclei. Second, this data is the ultimate stress test for our theories of physics. If our best models can't predict the properties of these weird atoms, then our models are wrong. Simple as that. And finally, we're literally mapping the edges of existence, finding out just how many neutrons you can possibly pack into a nucleus before it just falls apart.
And here is that stress test in action. That flat line at 0, that's reality. That's the actual experimentally measured masses of different lead isotopes. And those wavy lines, those are different theoretical models trying to predict those masses. As you can see, they get close, but none of them are perfect. This kind of precise, real-world data is what forces scientists to go back to the drawing board and build better, more accurate theories about how our universe actually works.
At the end of the day, this quest is about so much more than just filling in boxes on a chart. By exploring the most extreme, the most short-lived forms of matter, we are learning the fundamental rules of the cosmos. We are charting the very laws of reality itself. And the biggest question is still out there. What undiscovered lands lie just over the horizon on this map? And what secrets are they going to tell us when we finally get there?